Looks like that's working on the first try. That's kind of unusual. Definitely a good omen, though.
Good way to start the week.
Absolutely. Not any weird software issues. Oh, it's 5:30. Welcome back, everyone. So we're on our third week of the entire semester. We're definitely getting through it. And our work for today is, it suddenly got really echoey, by the way. If you're just joining us, I think they opened an event up there. But what for our work today, we're going to be finishing off chapter 2. We don't have too much to get through. And that's going to make our assignment number 2 officially assigned. Like we mentioned before, we'll only call these an officially assigned assignment the minute everything here has been finished off. And if we have to move the due date, we'll always make that happen. So the new due date is January 29th, a week away from today, since we'll definitely finish that section. I put here a tentative due date of January 31st, but if we decide we need a little bit more practice in chapter 11, we will take that additional time. Well, any questions, folks, before we get started? Yeah, go ahead.
Are the
Yeah, the exam dates will be really the major thing that's considered firm for dates. Absolutely.
do you do like a review for the exams or offer anything like that?
You know, if we look at our schedule, but one thing I did mention is it's a tentative schedule, which makes sense where sometimes a lot of the people who come to this class have different abilities and things like that. Sometimes we do different coverage potentially. The only thing that's firm on the schedules are exams 1, 2, 3, and the final exam, which will be assigned this week and then come as a take-home exam. And there is missing review dates right here, but I will be posting review problems. And if folks would like to look over some review ahead of the exam, it's pretty much how we start every class. It's opened up to student questions, student directed. And if it ends up we took that whole day discussing exam 1, then that's not a waste. That could definitely happen. So we'll mention that as we get closer and closer to that date. Looks like it'll be 5th of the February. On the Moodle website, it should be posted right here. And usually how my process usually works is I try to, once I get to this weekend, at the very latest, start posting information down there. It'll be the exact coverage, which chapters, things like that, and additional review problems. So you could ask questions about those review problems or other additional problems. When you come back to class on Wednesday of this week, that would be our opportunity for a review. Let me double check. No, hang on. Monday of this week, our exams are on Wednesdays. Sorry, it's a little different in each one of my classes. So when we come back on Monday of this, there'll be ample opportunity for review. And if we spend a lot or all the time reviewing, that's definitely okay. Olivia said, Pocatello students just make an appointment with testing center. Correct. Sort of, kind of the way it's going to work. And I'm going to be making sure everything is the same process for Pocatello, but it really has to start with me. I send Pocatello Testing Center a roster of students that will be testing there. Once they receive that roster and they receive the exam, they start to reach out to the students individually. Or I may have to send you a link to reach out after I've sent out the initial information. So as we get closer to this date, I'll definitely have that figured out. Around here, I'll be sending out the roster to the testing center. And then when everything's all set up, I'll reach out to you unless their process has changed a bit, and then you'll begin scheduling your exams. Does that make sense about that process at the moment, Olivia? Awesome, thanks. Question up here? You know, that's a weird thing that's kind of interesting about this class. There will be in-seat exams. So when we come back on this date, I'll just be here for 75 minutes, and people who can make it to this campus, to this classroom, you'll be taking your exams here. But there is an Idaho Falls Testing Center, and some of the people who are joining on this section are not necessarily around Pocatello. Some people might be closer to the actual Idaho Falls Testing Center. And if that's you, just reach out to me and I'll make sure that you don't have to drive too far for no apparent reason. So that's pretty much how it's going to work out. These classes are definitely weird when there's an in-person and fully online section, but we always get through it. It's not my first time doing these sort of things. Any other questions about the testing? Okay, well, with where we're at so far, we're about to finish chapter 2. Let me see if I can bring that back. There we go. After we finish chapter 2, because the course is majorly about statistical methods, we're not going to try to do too much probability. That really wouldn't be reused again in the course. Instead, we're going to go directly to the normal distributions. That's going to be one of several probability models that we really require. And on its own, I mean, this is a fun thing to work with. The good old normal distributions. But in all honesty, there's not a ton you can really do with the normal distributions, despite being told that lots of physical processes turn into something you can model with a normal distribution. The major reason the normal distributions have such a massive role in statistics is because of this theorem right here. Even if your data doesn't fit a normal distribution, if you're doing something with statistics, then you look at the sampling distribution of that statistic, and it turns out under the right conditions, even from a non-normal population, your statistic, like the sample mean X bar, still came from a different normal distribution. That's really pretty weird. It's extremely abstract. And it means every time you're sampling data, there are two populations. The populations of the individual that you're interested in, and there's a population of the statistics you could actually conceivably output from your study. So that's what chapter 13 is about. And because it's pretty abstract, in my personal opinion, it's the most abstract section of the book. This is a really good one to, at the very minimum, skim through it, and it'll help a ton when you come to class. Once we start saying these weird ideas like sampling distribution, your brain will already have kind of a extra help of extra traction of knowing what we're talking about. So we'll get through that after chapter 13. We'll begin our first honest statistical methods. But that's it for my announcements at the moment. Any other questions or comments, folks, before we jump to chapter 2? Okay, let's take a look. Not quite where we left off, but just kind of a really fast skim through what we did in chapter 2. We're defining statistics that we are going to actually calculate instead of in chapter 1, just say what we think the center looks like qualitatively. We can now calculate the sample mean and the sample's standard deviation and just get the center and spread described perfectly that way. But we mentioned these statistics have issues. We want to use the right statistic for the right study. And the homework assignment is very much about that. These two statistics require that your data be at least roughly symmetric. And if it's not, if your data is very skewed, we had to turn down to these kinds of statistics. The sample median just being the 50th percentile. It's the number that cuts off the lower and the upper half of the data. Highly effective against skewed data. And then we'll use the interquartile range. That's just going to be an honest range. It's a numerical value. It tells you the distance that the central middle 50% of your individuals lie across. So for very skewed data, we use those two statistics. Then the 5-number summary was also very helpful for us. If we ever want to use, say, the 1.5 IQ or rule of thumb to identify a suspected outlier, well, the 5-number summary helps. So does the box plot, which plots those 5 numbers, and it will reveal to you each and every time you have a potential outlier by that rule of thumb. So in the homework, if it's asking you to look for look for potential outliers, you could just use the box plot feature. And if that's missing, that open dot, you can say there is no potential outliers by the 1.5 IQ or rule of thumb, and you really are following the instructions to the letter that way. But that's just optional. If you like doing it by hand, you could just work out the statement here, and that's a fine way to do it as well. Yeah, go ahead.
That be a viable way to answer one of the assignment questions?
I believe so, yeah. I think there's a question about outliers, and outputting a box plot is a great way to do it. Other questions so far? Okay, well, we got through this problem here. We presented our data in this box plot, really just to get used to box plots and seeing outliers by that rule of thumb. And this is finally what we didn't get to. We just didn't run. We ran out of time and we didn't want to rush through it. This is meant to be kind of a cheat sheet of sorts. It's going to be really helpful in the homework. It'll be potentially useful when to think about these ideas when we come up to our exams. And we kind of filled in a little bit of this, but if our distribution is at least roughly symmetric, that's what we'll use for the center, the sample mean X bar, and that's what we'll use for the spread. And in these scenarios, the sample mean and the median do a pretty decent job of measuring where people think of the center. Clearly, the more you're skewed here, the less that statement is going to be accurate. But if it's at least roughly symmetric, then we think that that's a tolerable error in most cases. And here's a visual of at least roughly symmetric. It could start off great. Here's its main peak. It could start accumulating data fairly symmetrically around it. At this stage, if that's our entire distribution, I would say that this is very, very symmetric data. Go like this, and now we're breaking it a little bit. We have some rough symmetry. And let's see, if we add a little bit more going to the left, that might be the point at which it starts to become too skewed. Let's leave it right here. I would say for this kind of data, we would definitely pick these types of statistics to work with it. But if it's clearly skewed to the left, you're looking at things like these for your histograms. Let me try to do it a little bit less shoddy. You could have distributions that might potentially look like this. These could be outliers, they're pretty far away, but it's severely skewed to the left. In this case, the center would absolutely not be used. We need to use the median to measure the center. And because we're choosing the median, this is the next statistic that's just paired with it. Interquartile range. Well, once we put those down, another thing that's interesting is what happens to the sample mean X bar? Why is it we're not using it this time? Any volunteers on how you could relate them? Should the sample mean be larger or should the median be larger, in other words? Any volunteers over, say, Zoom, on which one ought to be the larger quantity? Oh, we got some responses. I agree. I believe the median on this one should be larger. And this is kind of an interesting thing that happens to the statistic X bar when we're dealing with skew. The statistic X bar follows the direction of skew. And you could think of this as an actual physical system. Imagine the axis as a 2x4. These things, you're stacking bricks or something with uniform density, uniform mass. And the location where X bar goes is where the whole system would balance. It'd be, say, the fulcrum of the system. If you have skew to the left, this has massive leverage, and X bar follows that leverage to balance the whole system. So in this case, we have that the median is the larger one. The sample mean got pulled to the left following that direction. And just to finish this off, let's do another quick picture here. But any questions at all, folks, with row 2? Okay, so now this one will be clearly skewed to the right. I think this one would be very severely skewed, but they don't all have to be really crazy cases. Let's do one where it almost looks symmetric, but it's skewed enough for us to decide we need this statistic, median interquartile range. So I'll put some data right here. Let's make it look symmetric to start. Now at this stage, that is massively symmetric data. It's wonderful. If this was your data, then it's not too bad to work with. Add some more distributions going to the right, and that could be a problem, but I would still say this is roughly symmetric. We might be okay here, especially if our sample size is large enough for the so-called central limit theorem to support us. But keep on putting data to the right, and at this stage, I'd become uncomfortable. This is looking like it's got enough skew so that the sample mean is not going to do a very good job. So at this picture, we would use the median for the center, interquartile range for the spread. If we compare the sample mean against the median, well, it's skewed to the right, so it would go this way. This time the sample mean is the larger amongst the two. So again, we mentioned that this table is really kind of just meant to be a big cheat sheet to help us with the upcoming homework assignment two. On the homework assignment two, you're going to be asked to calculate the most appropriate statistic to represent a center spread, but you really have to choose the right ones. If you have symmetric data, you'll be using this batch. Skew data, use these two here. Well, any questions at all, folks, with the end statements here? Okay, well, we did it, folks. That's our second chapter done. Let's save this up. Our process then is, after a chapter is completed, it does take me a while since I teach some pretty late night classes, but in the next morning, I'm going to come over here. This usually gets done before 11 a.m. Oh, not over here. I'm going to go over to chapter 2. I'm just going to overwrite these two files here with all the solutions that we posted or that we worked on. Well, let's open up our next chapter. We're now working in chapter 11, which is exciting, the normal distributions, which means this is our slow walk into dealing with probabilities as well. And we'll take our time with this one since I would say chapter 1, chapter 2, that's kind of the part of the course where we're really just introducing the course, getting everyone on the same page, learning software that is a bit clunky at first. But chapter 11 is where we're starting to pick up our pace a little bit. We'll still take our time because now we're trying to absorb probability ideas and those kinds of things. It gets a little bit weird, gets a little bit sketchy, but the same kind of problems you're going to see solved here are going to be pretty much the same sort of problems you'll expect on a homework assignment. And they'd be the same kind of problems you'd expect on an exam as well, except anytime I have to use RStudio to do a computation or a graphic, that would have been pre-done on the document for your exam. So you could think of this as pretty decent, honest exam problems right on this worksheet. Well, let's go through the notes and see what's going on here. It says, assume that a continuous random variable x, we're going to think of this as x is going to be the output to a randomly selected individual. Probably the data is going to be numeric and continuous all at the same time. We'll say it's distributed normally with a mean of mu, standard deviation of sigma. For these kinds of probability models, you're typically using the symbols that are describing parameters rather than statistics. We wouldn't use X bar and we wouldn't use S here. Then we'll say the probability distribution of X. Think of maybe X's heights of randomly selected fifth graders or something along those lines. That would probably be normally distributed. And here's how we would indicate it. This is some really clunky symbolism, so let's maybe put some extra space here and describe it. It's a decent shorthand, and it's also used quite a lot in the book, so it's absolutely worth getting used to. So here it's saying X. The tilde is read as is, let's just write out fully this way. X is distributed as so this portion right here is the tilde when we say is distributed as. Then over here we go normally with, and this is a little bit interesting as well. When you do an on this problem, it's not going to say mu there. It's just going to be a number. We have to know the thing that goes in the first position is always, put the mouse back, always the mean no matter what. So distributed with mean mu. And this one here is a bit interesting if you've done probability. Sometimes in probability, there's a convention of putting in the variance there. So that would have been a sigma squared. But statistics or the convention is more standard deviation. So you'll typically see just a sigma. If you've gotten a big habit of always putting sigma squared here, I'm not going to say you have to change it. That'd be okay. And I read it in context, oh, you're using the variance. So you don't have to change. But for the purpose of notes, I'll copy what the author does and always put sigma there. So we'll say mean mu and standard, STD for standard, DEV for deviation, sigma. So this right here, well, it's a really great shorthand. It's a great way to summarize what X is doing. But if you want to give the curve for it, here it is in blue. That's our normal distribution. And that's the function. It's a pretty nasty mathematical function that has some interesting properties. For example, let's zoom in just a bit more on this. Notice that the center, the mean, is that quantity right there. And you could think back in college algebra, This is a shift parameter. It's going to translate the exponential function either to the left or to the right based off the value of mu right there. You can put either positive or negative numbers in that location. And our axis is actually a little bit higher than you would think. Goes through like this. Oh, geez. Probably should have done that before class, but imagine that's a perfectly horizontal axis. Gives us a peak right up here. And that would be the location of mu in this setting here. Let's say mu is 0, since that's where it's located. Next thing we do is, well, if the standard deviation is sigma, then the formula will give us a sigma in this location, sigma squared in that location, and that does a whole bunch of things to the shape of this actual curve right here. It's becoming a bit of a distraction. Let me take that off. But one thing you can use with your sigma is, it is a kind of ruler or a yardstick. If you think back into calculus 1 on concave up versus concave down, what you're looking for on this curve is an inflection point. So we are needing to find where we're changing in concavity. You know what? That could be a decent classroom activity. Classroom activities are really hard in Zoom, but haven't forgotten you're there, folks. So for folks in class, as well as folks over Zoom, either using chat or voice, what I'm going to do is move the cursor across this curve. If you're a little bit rusty on calculus, no worries. Calculus is not a major part of this class. But if you recall what inflection points look like, just shout out stop right when it feels like we're getting close to one. So let's give this a try. If we miss it, I'll just come right back, so no worries. And there could be lag, but here we go. Tell me to stop when you think we've hit an inflection point. Right around here. Well, there wouldn't be an inflection right here, but there's a way to tell. One thing an inflection point has to do is cause a change in concavity. And that's already a weird statement, but right up here at the peak, we're concave down because this horizontal tangent line has the property that the curve is exclusively below it. We're concave down in that region. If we put a point right here, concavity is different. In this nearby region, the curve is always above that point, meaning it's now concave up in that location. So it went from here concave down, here concave up, and somewhere in the middle is where it changed its concavity. That's the inflection. So let's go through it again. From this dot to this dot, just holler stop when you see it might be a concavity spot. I'll try to pay better attention to the text. Sorry, I missed that, Aspen. All right, we're starting off. Definitely kind of tricky. It's somewhere in there, right? Probably a weird kind of activity. Midway, I agree with that reality. It should be about midway, right around here. That's the actual inflection point. Not easy to spot completely, but you get a feel for it the more and more you do these kinds of things. And really the major reason for trying to find that spot is, recall that sigma is the population's standard deviation. It controls how spread out the data is. So that sigma quantity, in a certain sense, is also a yardstick. The bigger the sigma, the more spread out. The smaller the sigma, the less spread out. And right here at the inflection, that would be where your sigma is. Whether this curve had a mean of, say, 20, standard deviation of 15, just ignore the whole axis, and you can find this location here, and sigma would always be about that far away from the center, its mean. Well, any questions, folks, with that curve here? Okay, we'll be studying and working with it, dealing with probabilities on it. And the probability model we're dealing with, kind of already hinted up here when it said a continuous random variable. Our probability model will be areas under curves much like this one. These kind of curves are referred to as density curves. So that's the terminology you're seeing right here. That's the formula for the density curve. And any honest density curve has a couple major features. One feature is, we can write it this way. We have a chat first. Let's take a look. Hannah said, you said The larger that sigma is, the more spread out the graph gets. Yes, that's true, absolutely. So in this graph down below, sigma was set to a 1, but if sigma was, say, 5, then this will just move all the way over to 5, and the whole graph would have to spread out to account for it. Other questions at the moment or comments? Okay, so we have a so-called density curve. That's this one here in blue. First thing your curve has to satisfy is the function is non-negative. You could write it out this way. The whole function without an input, then the whole function itself must be non-negative, greater than or equal to 0, meaning this can never dip below the actual horizontal axis. So that's a nice important feature. And the second feature is this. It looks weird, but you could write an integral sign, go from negative infinity to positive infinity, f of x dx. This is really calculus 2 kind of material, but if you've seen calculus 1, it's the same sort of integral. It just involves an extra limit to make it happen. This one's called an improper integral type 1 because there's not an actual real number there. It's saying find the area under this curve, but go to the left forever, no stopping. And that curve is always above the x-axis, it turns out, never even hits it because of the exponential function. Positive infinity says also accumulate the area to the right, going off forever. And if you really have a density curve, it's exactly 1, not approximately, not rounded to 1. The area under this curve is a dead-on 1. Kind of a weird fact, and that's why calculus 2 is required here. We find it's area 1 after taking the right limits to resolve this improper integral. So that's a major feature of our probability model. We have a non-negative, always positive. It might hit the x-axis on a different model, curve. Area under the curve is exactly 1. And now we have a type of probability space. But here's some extra features. This curve above, whose function is right here by the red dot, its domain really is all real numbers. The curve is always above the x-axis. It doesn't even touch it, no matter how far to the right or how far to the left you go. That's just a fact of the Base exponential or any exponential. These things never actually hit an x-axis. Like we mentioned, the total area is exactly 1. And this is the new thing. Areas under the curve will represent probabilities. In fact, let's illustrate it right here and now, our first probability. First, any questions at the moment, folks, absorbing this strange information? Okay, like we mentioned, areas under the curves that correspond to probabilities. So if we wrote something like this, let's take a value x here. And let's shade to the left of it, just a random example. I want area to the left. Then this area is the probability that, sorry, I need a better symbol than x, my mistake there. Let's go with k. We want the probability that the random variable x is less than k. To find that probability, it's going to be equal to this area. So that's essentially what probabilities are going to look like in this model. To find the area, it's not so bad. We would just integrate like this is saying, except that's actually a really, really hard integral. The methods for getting through this one involve calculus 3 out of nowheres, a change to polar coordinates, and all sorts of madness happens here. But you can really get this and get area exactly 1. Other methods, well, you could use, say, the left endpoint rule, right endpoint rule, or midpoint rule, all those approximation methods to find the areas. That's extremely tedious, and you could build out a table of values like they did historically. Or you could just use RStudio. This has been implemented with extremely good numerical procedures, and we'll find the areas under this curve immediately. Even though there's no great antiderivative to this, no elementary antiderivative at all to this function, RStudio doesn't have a problem getting approximate areas with high accuracy. So this is the kind of introduction to chapter 11. Our goal is to play around with these, get familiar with this probability model, how it works, plotting with it, and then we'll do some probabilities as our last final questions on these notes. Any comments or statements at the moment, folks? Okay, so here's our next thing to take a look at. So we're going right into a situation where we would model a population using a normal distribution. It says here that a certain population of the herring Columbus estivalis, something like that. Let's take a look at that. One thing that you could do if you're ever looking at a weird context in a statistical study, you could just say, right click on it. Let's search that thing. It's supposed to be a bird. It said herring at least. Or what in the world? Population of the herring, Polobus estivus. It looks like mushrooms. Maybe a better way to do this is just an honest Google search. Let's take a look. I was not expecting mushrooms. There we go. So that's what we're looking at. So we're looking at the herrings like these. It's kind of silly to do something like that, but really when it comes to statistical problems, the hardest thing is about the context, and anything you can do to kind of place yourself inside the context, looking at the things you're even studying, it really helps out a great deal, especially when we're going to write out conclusions to statistical problems. So that's what we're dealing with in this problem, and it says, the lengths of individual fish follow a normal distribution. We're going to assume that the population's mean length of the fish is 54 millimeters. From that statement here, might not be a bad idea to begin by writing out mu is 54. And the population standard deviation is 4.5 millimeters. So sigma is 4.5. Well, we don't necessarily know that these are the accurate facts about the population. They could be some really great estimates. What we're trying to do is model the population just based upon the best information we have. And looks like that's the best information we have. It tells us first, what is the probability distribution of X? That's always a tough question. I've been teaching this course since about, I think, 2014, and I always get the most questions about this. So let's highlight it in yellow. What is even being asked when you're told what is the probability distribution of X? Well, X is right here. X is a random variable. It's going to denote the length of a randomly selected herring from this population. We just want to know what is its distribution. They told us it's, let's see here, follows a normal distribution, so we want to mention that. You could just write this out normally. You could say X is normally distributed with mean u equals 54, standard deviation sigma equals 4.5. Put the unit on that last one. Writing out in ordinary words, completely fine, always full credit. Let's call this option 1 for your response. Option 2 would be to say just simply this. You're just really going to paraphrase all of this using symbols. You'll write out X. This is referring to the random variable. Let's put that in blue just to emphasize. Put in the tilde here. That tilde is just saying is distributed when you go to write it out. So pretty decent shorthand there. We put an N to mention it's distributed normally now, giving that right information. First thing we put in is always the mean when we specify it this way. So X is distributed normally. Its mean is 54. You could put the units in there, but I usually leave them off if I'm writing it out in symbols like this. And standard deviation is 4.5. So you don't have to write out both ways. Either way you're most comfortable with is just fine. But I would encourage you to just get fluent with recognizing this visually, since it does come up throughout the book, throughout the lecture notes. That'll be a pretty common shorthand. So we did it, folks. That's our normal distribution. And for part B, it asks us, sketch the graph of the density curve F for this distribution. That means we're doing this kind of graph, like the one above. When you do this in homework, you're absolutely fine to just freehand it. There's no problems ever with doing that. If you do decide to do a freehand sketch, the tricks are definitely don't go like this, because this would definitely not be a normal curve. It's non-negative, so your curve can't dip below the x-axis. Another thing that's weird is we usually don't do the vertical axis. There's less exciting information there. We only care about areas. Anything that looks about like this would do the job. Doesn't have to be perfect. It's losing symmetry. It's concerning right here. But as long as it's not doing anything massively out of order, I wouldn't be too picky. A whole different option, if you'd like, is if you have to sketch a graph. This would definitely be a homework problem, not an exam problem. You could use this syntax right down below right here. So this is for coming up with a plot on RStudio. Plots on RStudio are kind of awkward, so that's a lot of stuff to plot something. Or you could use your favorite programming language to plot your function. If you grab this right here and you decide to use RStudio, this is how it would work. This can copy directly out of Word, since I didn't type it there. It's got the right formatting. Next thing you want to look up is this right here, where we specify the model, how X was distributed. Move this temporarily here. Now back in RStudio, I'm just taking all this syntax we copied and let's directly just dump it in. There's a lot of stuff being stated here. Anything that starts with a hash and is written down in green is really just a comment. So there's a lot of comments going on. It says here, first define the parameters of the model. This is set to the standard normal distribution with a mean of 0, standard deviation of 1. But from what we said right here, we need to update the model for a mean of 54 for mu and a standard deviation of 4.5 for sigma. And pretty much that's all you have to change in all the syntax, just this field right here. The rest of it is going to do some strange things. This is how they define functions. This is how we're going to get a plot by specifying x values, feeding the x values into the function to get the y values. But then this just does the plot with some bells and whistles. Full disclosure, some elements of this code, particularly right here, this is all ChatGPT. They helped me out with this to make that work out for us. That's a great option a lot of times if you're trying to do something new. And here it is, that's our model. It should be centered at 54, so that looks about right from here. The standard deviation is 4.5, so if I go to about here, this should be about 4.5 away from the center. Project down. Yeah, that looks like it could be about right. I might not pick the inflection point perfectly, but definitely looks believable. So here's our plot. Let me try this one more time. Copy to clipboard. I haven't been having success copying it as a bitmap, so let me try it as a meta file. Copy plot. Let's see what that does for us. It works in my home office, so I'm kind of not sure what's wrong with the update. But I guess that's it. If you use a meta file, if you're having my same issues, then it does actually plot in just fine. Let me show you how that worked in case I did that a little bit fast. So when I usually get my graphics out, pretty much I'm just using a snipping tool. It's the Windows Shift S key. I just grab this much and go with it. But sometimes it's fun to just go click on export, copy to clipboard, and you'll have a lot more control just moving this around, resizing it however you like. The default's a bitmap, and on this machine, that doesn't actually work. So try this workaround. Go to Meta File, click Copy Plot. See if we can update this one. And then you should be able to paste this in, Control V, and there's our distribution. Looks kind of wonky, it's really wide, but you know what? It fits our formatting. We have low vertical space, a lot of horizontal space for this class. Only thing I don't like about that method is there's a lot of white space here, but that's not a huge issue, truly. What we did, folks, it said sketch the graph of the density curve. Now we have it, and that's the reason we're doing these kinds of things is when we get pretty far in probability and with our statistical methods, sometimes these models, like the normal distributions, they become like a black box. We feed in information, we get information back out. But in statistics, if you have a picture on the back of your mind, whether you drew it out or not, you can judge the accuracy, veracity of that information to tell if there was a mistake. Maybe I mixed up mu and sigma, my output looks funny, because I know what the picture should look like. My probability is either too big or too small based off the information. So that's kind of our idea with what we're doing here. working with the normal distribution just to get a feel for what it looks like when we get further on in the course. Also, we're trying to get used to probabilities and not actually seeing the model when we're dealing with areas for probabilities. It seems like a disservice. We should see the model for dealing with areas. So let's see what part C is saying. It says, the probability that a randomly selected fish from this population, they're referring to X when they say that, and that's where this scale right here comes from. This is really a X-axis if you'd want to superimpose it there. It's measured in millimeters, that's a pretty small fish. So it says the probability that a randomly selected fish from this population has a length less than 50 millimeters is this, a probability of 0.1870. The way it's written out, it's kind of interesting. We put down P to say probability. This is now function notation. The parentheses are indicating of, so probability of something. The input is a set rather than a whole number. We want the set of all X values directly less than 50. Probability coming out of 0.1870 means the area under this blue curve to the left of 50 is 0.1870. Total area is 1, and you could say it's 18%, 18.70% of the area if you'd like. So it says, for an interpretation of this, there's an 18.70% chance of randomly selecting a fish from this population with a length less than 50 millimeters. So that's the practical interpretation here. And I have actually assigned this as a concept question for an exam problem. Reason I'm mentioning that is that's not been the most successful concept question, but it is a potential for coming up again, either on exam 1, maybe a final exam question. So when it says shade the portion of the graph corresponding to this probability, we'll go and take this information, less than 50. On 50, I'll put in a vertical bar going this way and shade to the left. Let's do some really kind of low effort shading. So this area of 0.1870 is what goes right inside of there. And that's again how our probabilities are going to look like when we're using the normal model. Any questions at all, folks, with that there? Okay, I would say the most important takeaway with this first example is getting used to the notation and getting used to visualizing our probabilities as areas, what they actually look like, and setting them in. So next thing we have is some strange concept questions, starting out with part D. It says, explain why the probability that X equals 50 must be 0. I notice there's already a weird conundrum here. When I drew that line, somebody thought that's not even drawn correctly. It said probability X less 50. Maybe it should have been a dashed line to say the area is not on that line, it's to the left of that line. But then the second statement is, what is the area of that line? It would have area 0, right? There's no width to an actual line. And that's what's going on here. And it's a defect in some sense of any continuous probability model where areas become probabilities. You might be interested in a single event. Maybe 50 is something interesting, but the probability of selecting a herring from this population with length exactly 50 millimeters is directly 0 by this model. The model cannot resolve one single observation. It requires a range of values. So maybe from 45 to 50, some interval of values, never a single point. So here the issue is the area of a line is 0. And so probability X equals 50 must equal 0. And I'm writing a little bit bigger than I thought. Let me pull in some extra space. That probability must equal 0, since probabilities are areas. So again, that's really kind of weird. All of our interesting probability statements from these kinds of models will always be a range of values. These questions, even though they might be the most interesting question you have about the study, they cannot be ascertained by this model. It's always probability of zero. You're not getting any intuition from that. And it becomes even stranger. If you look at this statement again, your practical interpretation is that a randomly selected fish from this population has a length less than 50 millimeters. That's just one interpretation. You might have said less than or equal to 50 millimeters, and it's still the right interpretation. Because right at 50, it doesn't change the probability. Usually when I go to write my interpretations, I usually just say less. Even if it was a less than or equals here, it would make no difference in the probability. It makes no difference in your interpretation. Bizarre. And to take another look at that bizarreness, let's take a look at part E. Explain why probability x less 50 is the same probability x is less than or equal to 50. It would essentially go like this. Let's start on the right-hand side, probability that x is less than or equal to 50. Inside here, we're just dealing with a set. And we can break up the set however we like. Let's break it up by saying probability. Either x is strictly less than 50 or x equals 50. Another thing you can do in probability is whenever there's an or, which is conflated with a union symbol, if you prefer using that notation, you can break this up as long as this set is mutually exclusive with this set, not overlapping. It's absolutely true. X less than 50 doesn't include 50 at all. So we can break this up and say probability x less 50 from the or, this turns into a plus. Probability x equals 50. But we already know probability x equals 50 is directly a value of 0. And so here's our last statement. The probability that x was less than or equal to 50 settles down to being exactly equal to the probability that x is strictly less than 50. Very, very strange. Really, part E is just another way of looking at consequences of part D. One specific point makes zero difference in your probabilities in this land of probability models. Well, that's looks like the last of this question here, folks. Any questions or additional comments about normal models at the moment? Okay, we've got enough time, it looks like, to actually start calculating out some stuff. So think of, again, example one, we're just getting started. These are the kind of concepts we need to have in the back of our mind. Next, as we go to start calculating things, I put this here since sometimes it's just as important to know how to use the normal model as it is to know when you can model a population using a normal model. So here's the 68, 95, 99.7 rule. I'm not going to ask questions about this rule directly in homework nor exams, really just here for another way to visualize the normal distribution and where all the probabilities would land. But the bigger takeaway of this is right here. It says if a data distribution is mound-shaped, sometimes we say bell-curved or unimodal for that word there, at least roughly symmetric, that's us being forgiving, a little bit of deviation for symmetry is okay, then the data may be modeled using a normal distribution with the correct choice of mu, or just the most optimal choice we can find, and the most optimal choice of sigma. Here's a reiteration of what we mentioned before. When we place those values of mu and sigma, we're not saying we know those values exactly. We're just relying on the best information to give the most accurate model we can give. We're almost always assuming that these are not accurate. We're just trying to do the best we can with available information. Then, if you're modeling data with a normal curve, you'd find about 68% of all of your observations in the population should be within 1 standard deviation of the mean. And like we mentioned, that's the inflection point right there. 1 standard deviation turns out just to be a great ruler. You'll have about all of your observations within 2 standard deviations, and 99.7% of all of your observations for area under the curve would be within 3 standard deviations. What this is essentially saying now is anything that's beyond 3 standard deviations starts to look highly, highly unusual, almost certainly flagged by the 1.5 IQ or rule of thumb as being a suspected outlier. And again, those are the remarkable individuals, more than 3 deviations in either directions. So again, that's what the normal curve looks like. But this is the big takeaway. Your data must be mound-shaped and at least roughly symmetric. If it's not, the model, you can use it, but your conclusions on the model are most likely going to be completely nonsense. If people checked out to what you said and what actually happened later on, they would detect that there was some major problem with the model. So let's take a look at this next problem, which is pretty much all about that. Let me get to this portion. So we looked at these data before, and I believe this graphic was one we produced as a class. This was a reminder, this came from veterinary school. It said, an anatomist investigated the spatial arrangement of the nerve cells in the intestine of a pony. He removed a block of tissue from the intestinal wall. He cut that block up and just counted the number of nerve cells. And here's that data displayed in a histogram. So the whole question on this one, this could potentially be an exam question. It's also a homework question. We're being asked, is it reasonable to model these data with a normal distribution? I will have to explain as well. First, let's make a decision on this. Would you all say it's at least roughly symmetric, or is it highly skewed? I would agree with that. Yeah, absolutely. Even if I had an observation out here, start to have a sense of skew to it, I would still call that roughly symmetric. So let's start by saying these data are symmetric. Mound shape just means we're trying to exclude data that might look like this, for example. These data are important. They're kind of unusual depending on what you're doing, but they can come up. This is data that's considered to be uniform. But in other words, not mound-shaped. So the reason mound-shaped is so important is you can imagine if you were going to put a curve to say these data over here, the curve should probably look about like this. It needs to come up, peak around where your data is peaking as well, then come down. Definitely didn't model all of the area in the histogram perfectly. There's a void region here. There's a region here that's above the actual curve, but it didn't do a horrible job. However, for these data above, if I try to do the same thing, my curve is almost always going to do way worse than what you're seeing down here. There's a lot of data that's mismodeled in this location and in this location, a lot of white space up here. But for these kinds of data, if it's at least mound-shaped, you don't run into that same kind of problem. So down here, we'll say these data are symmetric and mound-shaped. And so it is reasonable to use the normal distribution. Well, any questions, folks, with this statement here? Okay, so this is, again, kind of a good situation to be in. If all you're trying to do is model a population, if your data looks like this, you have evidence that the underlying population itself might be following these features, mound-shaped and normally distributed. We would look for the right values of mu and sigma to just give our best approximation and start modeling the population. But then imagine you try to do that again with these data. This is another problem that we saw in the notes the other day, just kind of redone here as an additional problem. This is the 2015 Urban Mobility Scorecard, and it's telling us the amount of money wasted directly due to traffic congestion in these major cities. So for example, if you look at just this rectangle, that means, well, the height is at 1. That means there is one city that experienced between 12 and 14 millions of dollars of loss in 2015 due to congestion. So it's important to model these data since this is a lot of money being wasted. We want to keep careful track of that and see if the situation could improve. But would you say we could use the normal distribution for these data? I agree with folks in class, it's looking bad. How about for folks in Zoom? What would be your first thing you'd want to say? What's wrong with these data? that you wouldn't want to use the normal distribution. I agree with Olivia, they're skewed, and Hannah as well. That's pretty much the major takeaway with this. Once things look definitely skewed, there's no way I'd call this roughly symmetric. We've got a problem. And it's a lot of problems now. If we, for example, are trying to model these data, you cannot use the normal distribution. Good news, there's other distributions. This one could be modeled by the so-called exponential one, if you're curious about those kinds of models. So like folks fed in class and in Zoom, it is not reasonable to model these data with a normal curve, or you could say normal distribution. Let's go normal curve. Since the data is skewed to the right. Really, you didn't have to say the direction of skew. It's just kind of normal to say what direction it's skewed in. It's the sole fact that it was skewed that makes the normal model not work. And here's the big problem with it. If we did try to put a normal model on this, the peak of the model should match the peak with the data right here. Let's extend the scale just to make its shortcomings look a little bit more apparent. So my normal curve, the best I could potentially do to it, would look about like this. This is not the best drawing, but we'll go with it. It looks like it's doing okay on this side towards the right. It does seem to model these data okay, but it's going to miss these observations in a certain sense. These are extremely unusual for a normal distribution. But here's our big problem. If it's skewed right, you have half the area of the normal curve just about that's not modeling anything at all. It might not even make sense of the problem. So that's the major reason we just can't use a symmetric curve. We need a curve that matches the skew. Let's take that off so it doesn't get too overwhelming on the notes. But any questions or comments at the moment, folks, with these examples so far? Okay. Oh, we do have a chat. Zachary says, so if the graph is not mound-shaped, but symmetric, then we would not use the normal distribution. Yeah, that's a good question to return to, Zachary. That's these data up here, uniform data. It is pretty unusual, and I think really the only example I can think of where you would get uniform data is random number generators from, say, 0 to 10, something like that. If you have a good random number generator, you'll expect a high degree of uniformity here. But let's add that comment that you mentioned. This is uniformed, not mound-shaped. And so here, we cannot, let's say, I mean, we can, but we should not, it's not well modeled by the normal distribution. Here we should not use the normal distribution. I'll use DIST for distribution. And that makes sense too, because really, if your data is uniform, you should be trying to model your data with a straight line, not a line that's going to be curved. So the normal model is definitely just not even the most sensible choice in hindsight. But other questions about that so far? Okay, thanks for asking that question, Zach. So far in the notes, we really haven't calculated anything, if you might have noticed. We've looked at the normal model, we've looked at notation issues, interpretation issues. We've looked at when the model is appropriate. Here, it's great. Not so great here, we lost symmetry. But the next thing we want to do is, let's now start actually calculating things out, beginning in example 3. Before we get too far, I do want to point to a couple places on the notes that are helpful. So on chapter 11 with the normal distributions, one thing I try to always include if we're going to come up to a new distribution, we'll see T distributions, F distributions, and so on. Always include a file that goes like this, our syntax. And what I include in that file is anything that you might need for homework whatsoever. If there's an operation in the homework that's missing here, I need to update this document and bring it in. So if you want the probability that X is less than A, we'll calculate using our syntax by saying P. P for probability, that makes sense. We're using the normal distribution, so we'll call it P norm. The value that is in the probability statement becomes the first input to the function, and the last two inputs to the function, not necessarily the final last two, depending on what you're doing, but here the last two inputs from the function come from here, the model itself. So that's how we'll find the probability that x is less than a number. We want to find the area to the right. We'll just turn lower dot tail equals false, kind of strange. Probability between two numbers is not very nice in RStudio. This one's a little bit clunky. You calculate twice. And we'll come back to these two where we're solving equations. So this is a good one-stop shop for just looking up something quickly in RStudio. But I'll always try to include those kinds of files. And like we've done before in notes, anything we do with RStudio syntactically, I'll always copy that syntax and place it in the document. Let's see what we're getting into then before we begin. It says the time it takes a driver to react to the brake lights on a decelerating vehicle is critical to helping avoid rear end collisions. That's context, so here's what actually happened in the study. The article Fast Rise Brake Lamp as a Collision Prevention Device from 1983 suggests that reaction time for an in-traffic response to a brake signal from a standard brake light can be modeled with the normal distribution, having mean 1.25 seconds and standard deviation 0.46 seconds. So kind of the idea with this study is, it looks like participants were in kind of like a mock car setup. They're supposed to have the brake lights as soon as they observed a brake light in front of them, and we're just measuring reaction times. In this study, we have two statistics, but because we're going to model the data, we're going to think of these as parameters and write mu is 1.25. Actually, let me put that over here. Mu is 1.25 seconds. And from here, where it mentions a standard deviation of about a half a second, let's write out sigma equals 0.46 seconds. Next, we have a random variable. It says here, x is going to be the reaction time for an in-traffic response to a brake signal from a straggling brake lights from a randomly selected driver from this study, it says. The wording here is kind of interesting. When they say we're selecting a driver randomly from this study, it means all the study participants, they're now the population. And that does make sense. That's now a population mean. We've redefined who we think the population of interest should be. We're not trying to model everybody. We're just modeling people in the study, no one else. These parameters are now actually fully accurate, but these are rare settings in statistics. It's typical. These are just approximations. First question they ask is, what is the probability distribution of X? Always a confusing question, but I typically answer them this way. You mention X. This is saying X is distributed as. Next symbol, we tell them it's distributed normally. And now we have to put a first value here. Would it be 0.46 or 1.25? Anyone recall what goes in first with our notation? Exactly, we have to put in the mean first, so 1.25, like you said. So I'll go 1.25. And I usually don't put in units here, but that's a personal choice. If you think it helps to put in the unit, maybe it probably does. It reminds you of the context, then go for it. That's really a stylistic choice. So 0.4 seconds here for the standard deviation. So now we've got it, that's our model. And you know, once you write out this much, not a bad idea to come back to RStudio. Fix it for a moment here. Usually that works when you double click up there. The way we're going to use RStudio today is very much like a calculator, so we don't need any fancy graphics. And I would start by inputting these values. So let's write in mu could do the job. Mu gets 1.25. For sigma, I'll just type in short sig. Let's redefine that as 0.46. And well, at least we have some models or some values stored in. Then back here it says, calculate the probability that X. Let's always recall when we see that X there, that we're we're referring to this one up top. X is just a reaction time for someone randomly selected in the study. We want to know for this random participant, what is the chance that they took between a second and a second and a half to respond to the brake light? And you can imagine this is pretty high stakes, right? We are driving home. This is stuff that we worry about all the time. Is the person behind us going to take almost 2 seconds to respond to my brake light? That could be a bad deal sometimes in Idaho Falls. Well, the first thing you might do when you take a look at this kind of thing is you could just put in the syntax, directly calculate it. You might have only given me a number here. You also have to give the practical interpretation. But when you're starting to learn this kind of stuff, a really fast drawing is not a bad idea. Even professional statisticians that do consulting for corporations, they do this kind of stuff because if you're organizing your information, that's never going to hurt. Next thing I might put down is 1.75. Actually, let's put in the center. 1.25 seconds, so it's going to be right here. The actual question is relative to between 1 second and 1.75. So let's just place them as best we can. We're not trying to place them perfectly, but we know the standard deviation is about 0.46. So right around here would be about 0.75-ish. You need to be right around here then for a value of 1. But again, you don't have to place them perfectly if you're doing this sketch. In fact, the whole sketch is optional. But here's our first value, then it's 1.75. That is not exactly a standard deviation away, but it's pretty close. So I'd put it about here. Now we have a horizontal axis, but that horizontal axis is X, and this is measured in seconds. Let me do a little bit better with this highlighting here. So whenever X is being mentioned, it can be manifested in a lot of ways. Inside the probability statement, you don't have to put it in your axis, but it's a great reminder. And now the whole answer to this, probability 1.00 less X less 1.75, it's just going to be this area. So that's our answer right there. Now let's make RStudio do the heavy lifting for us. So back to RStudio, to do this kind of probability, it's one of the more clunky ones. First thing you want to do is always go to the upper value. Type in P, we're doing probability by saying that. Norm is specifying the model, the normal distribution. First thing we give it is not the actual parameters. We give it a value on that horizontal axis. So you want to give it the upper value first, 1.75. Then the last values are these two. But you're probably calling up probability a lot in this. That's why storing them above is pretty helpful. I usually just put in mu sigma and write out my answers this way. So I'm really only stating the parameters once. That helps out because if I have to type these out multiple times, I'm going to mistype it somewhere, somehow, eventually. So if you read it this far, it tells us that the probability, it's absolutely wrong, but let's take a close look at it, is 0.861472. That would say this area is about 80% of the area. That's definitely wrong, right? What's happened was RStudio took this value and then took all the area going to the left, not stopping here, it included this area. So let's just put a temporary mark here. I'm going to delete this in a moment. But what we need to do now is eliminate that area highlighted in the, I guess that's purple pencil tool there. And we do that by stating p-norm again. Let me just fix this window real quick here. So if we take p-norm from here, we'll eliminate this area as long as we put a minus in between. So start with p-norm at 1.75. We got that probability or area to the left. Subtract probability with the normal distribution starting at 1, mu and sigma. And this portion here eliminates that highlighted area that we never wanted. But again, if you draw these pictures or just visualize them in your mental chalkboard, the answers you get down here you can really judge if they're even correct in the first place, if they're even remotely reasonable. So let's run this. It says the area from here to here under the curve is about 0.5680. I would believe it at that stage. It is a by hand drawing, so I'm not trying to look for perfect looking area. But if it's in the right ballpark, you're probably in great shape. So let's take this. I want to place this here just to say this entire statement gives this area. So that's what we need to do to get the result. And when you're giving a statement of probability, usually, unless instructions say otherwise, but I think that's going to be atypical, usually 4 decimal places is a routine and decent amount to round to for probabilities. So let's call this a 0.5681. Well, we did it, folks. That's our first probability computation. We still have a little bit more to do on this problem, like this portion right here, give the practical interpretation. How about we make that the last part of class today? Does that sound all right to folks? Okay, I put that in purple and made a big deal out of it. Not because it's been a big deal so far. You've seen those instructions in the chapter 1 assignment, for example, but wasn't really any cause to grade this so very harshly so far. But with statistics, we'll be doing a lot of these kinds of things. We have to interpret our hypothesis tests. We have to interpret our confidence intervals. If we interpret a probability statement here, that is remarkably similar to interpreting a confidence interval. So this is a lot of practice in the right direction for something we'll do a lot in this class. The way I would interpret it, and this is a lot, just one option, I would start here. And when we say practical interpretation, we want interpretation you could say, give to the news, for example, and lay people to understand whether they took probability or not. So I wouldn't say there's a probability of 0.5681. That gets a little bit foggy. I would say instead, there is a 56.81% chance that. Then the next thing you want to take a look at is what was X? It's right up here. We can say that the reaction to a break signal. Notice I didn't copy in everything there. It's okay to be a little bit terse and let the context right here carry your statement down there. So there's a 56.81% chance that this reaction time here to the break signal is between 1 and 1.75 seconds. Is between 1 and 1.75 seconds. So this right here is what we refer to as the practical interpretation. I usually start with a probability, convert it to a percentage, and really just mention X, and then read it out left to right. X is between those two values. Again, drive safe out there if you're driving today. That is a lot of time if the roads are slippery, almost 2 seconds. And it's suggesting, well, this is only for the participants in the study. If it does apply to everyone else, that could happen more than half the time. Pretty rough. Well, any last questions or comments, folks, on getting through this one? Okay, I put down some syntax here, but the way I'm going to do these notes is, if there's multiple parts, I'll typically go like this. I just give an overall syntax to the entire question at the very, very bottom. So we don't have weird snippets like this all over the place. But looks like this is probably a good stopping point for us, folks. If you have any other questions, I'm available for just a bit before my 7 o'clock class. I'll be happy to help out. Otherwise, I'll see you all on Wednesday's class. Thanks, Olivia, and thanks for everyone's participation in class today. It's tricky with Zoom, but we'll make it work somehow, some way. Have a good one. Thanks, you too, Zach. Thanks, Aspen. You too.